Oh, because the mic was already on. Hello. I see there's a few viewers out there for the live stream, so nice to have you. Thanks for being here as always. We're in week 13, so just a heads up about next week for you guys is a review. Um, so I'll probably sort of dig in on the second project in terms of giving you some tips about what's required, what's expected. It's all written, of course, in the specifications. You don't actually need that from me, but that's what I'm going to do is just kind of review um, the the knowledge and skills that we've covered up to this point and focus on those that will be most helpful to you in being successful in the second project. So that's what happens next week. This week is a normal week. But if you're feeling anxious because you have got like if you're in a PNA 2 class with me as an example, then you probably have a project due this week. So anyway, that'll give you some relief there. Well, this week a little bit. At least it gives you a little bit better of a break. Okay, so yeah, let me go into one of these and get us oriented. So I don't have a huge amount of content today, which is probably always welcome. Um, we are in the week of November 14th, so we're doing memory management and pointers. So pointers don't look like pointers in HLA, in assembly language. Um, but all a pointer is a memory address. And it's a pointer is just a variable where a memory address is stored. So when you declare a pointer in a language like C++, all you're doing really is declaring a variable that is designed to store a memory address. And then C++ has special syntax for dereferencing the memory address to get to the data at that memory location. So does x86 assembly slash HLA has a special syntax for that. So you use the square brackets when you have an address and you need to get to the data that address is referring to. So that's what we mean by pointers. It's an address in assembly and it is dereferenced with square brackets in x86 assembly. Memory management is kind of a high level technique, although you need it in assembly too, which is the ability to allocate additional memory when the program is already running. What most of us do for much of our careers in computer science up to a point is that we always declare variables and arrays and things like that to represent all of the required memory for our programs. And that's great while you're in school, but in the real world, we usually have to write software where we have no idea what the memory needs of our program are going to be. So we need the ability to allocate memory on the fly, as it were, allocate memory to accommodate data as the program is doing its work and as our algorithms are discovering the need for more memory, then we have the ability to allocate it as needed. When we say memory management, there's two sides to that. So there's allocating it, and then there's also deallocating it or freeing it. So when you, in a language like HLA and C++, when you allocate memory manually, you have to deallocate or free it manually, or you cause what you've all heard of is a memory leak. So a memory leak is simply allocated memory that you lose a handle on and you never free it, and it becomes a consumed resource on the computer as long as your program continues to run. Once your program is shut down, whatever wasted memory you had will be reclaimed by the operating system. But it's you don't want to get in the habit of just saying, well, I'll shut down my program and whatever memory I was wasting in memory leaks will just be cleaned up anyway, because a lot of us end up running software that will run for a very, very, very long time. Even, for example, if you were working on a web browser, let's say, and someone opens the web browser and then they open a bunch of tabs and they just leave the web browser running like that for hours or days or even weeks sometimes without ever shutting it down. If that software is allocating memory and leaving memory leaks, that will eventually have an impact on the performance of the computer. It can cause problems. So you want to learn how to do memory management properly. And that's one of the things that we do here this week is practice the techniques and the sort of the planning involved in allocating memory at runtime and deallocating or freeing memory at runtime. Okay, individual project 2 is due on November 11th, which seems like a long way away, but it's not really a long way away at all. In fact, 1, 2, 3, 4, wait, 1, 2, 3, yep, at the end of 4 more weeks. And then we have 1 more week of content after the second project. So it's 1 more lab, 1 more homework, 1 more discussion in the last week, where we look at how our floating point values done on modern processors. I find it interesting and very difficult, but it's good insight. So anyway, that's what's coming up. So let me get into this module and look around. Hopefully, yeah. Just checking all my sound and whatnot. Okay, so HLA actually has more than just, this is called malloc, what I've highlighted on the screen. So in the C language, it's also called a malloc. That stands for memory allocation. But you'll hear C programmers use the term malloc, and when they say malloc, they are talking about dynamic memory allocations. In the C++ language, we use the keyword new to do that. We also use the keyword new in several other languages, like Java uses new to allocate memory. And someone in one of the sections has already written a very nice discussion piece to get this week started. So while I'm sitting here looking at malloc, I'll just talk about it briefly. A language like HLA, and this would be true for assembly as well, languages like C and C++, those are languages that require manual memory management. And by manual management, what we mostly mean is that the programmer is responsible for deallocating memory. The allocating memory on the fly, many languages have that. The manual memory management is really attached to the concept of having to free the memory, pardon me, when you're done with it. So C, C++, HLA, x86 assembly, they all have manual memory management. You allocate memory as needed on the fly, and you deallocate it or free it when you're done with it, or you cause memory leaks. Languages like Java, Python, Go, many others. You'll see this in the discussion. Ruby does this. Many languages have garbage collectors built in or garbage collection systems. And in those languages that have garbage collection, you can still allocate memory on the fly, but you don't have to clean it up for yourself. Those languages actually run little subsystems that keep track of your allocated memory, and they free it for you when you're done using it. So when people first encounter that concept, they often will ask, why don't all languages just have garbage collectors? And you'll see one of your classes, and hopefully the other class will get a good quality introduction to the concept of garbage collection. The reason why not all languages do that is because that running that subsystem trades off a lot of efficiency. So it consumes memory, it consumes processor time, and it is basically another running piece of software that has to keep track of your memory usage at runtime. So for the most sort of the fastest, most efficient software, garbage collectors aren't always desirable. They do head off the problem of memory leaks, but they add the new problem of less efficiency. All right, so anyway, that's where that is. HLA is a manual memory management language, so we allocate and we free manually, and if we don't free when we're supposed to, then we cause memory leaks, which isn't a huge deal for us, but it's something that you want to learn how to do properly. Okay, so we're going to use dword variables to track memory addresses. So HLA and x86 assembly don't have a syntax to represent a pointer specific. Well, that's not true in HLA, it does, but we won't use it. We're just going to do the assembly style, which is that pointers are really just have to be tracked as memory addresses, and you have to remember that those variables are being used to store memory addresses so that you can manage your memory through them. So pointers are the way that we manage the memory and also use the memory when we need to store or retrieve data from memory. What else do I see on this screen? Addressing modes. So I'm most comfortable with scaled indexed addressing when we're doing array type stuff. Of course, that is a variant of indirect addressing. Anytime you see the square brackets in our class, we're doing some form of indirect addressing, which means that we have an address and we are dereferencing it to get to the memory location it represents. And then we have indexed addressing, where we take an address and then we add a byte offset from it, which is most useful when we're trying to access array data. And then we also have the style, the indirect style, where we have a base address, and then we add not a byte offset, but an index that is scaled to match the data type of the underlying array. So scaled indexed addressing allows us to use sort of the traditional zero-based index, and then we use the scaling factor to ensure that we're getting to the right location in memory off of the base. And then last, we'll use calls to free to release memory when it is no longer needed. Okay, so just a couple of short readings. I'm actually going to pop open this memory one and come back to it. Homework as always. Lab, I'll go ahead and pop that open and come back to it as well. There's only one kind of thing that I think is a challenge at all intellectually of the lab, which is to figure out what the data type of the array is. So we'll use context to figure that out. And then one of the classes has already got a good sort of launching point. Someone's already gone in and done a really good introduction to garbage collection to start that discussion. So hopefully someone will do it in the other class as well. But pointers is something that, for those of you who haven't taken PNA2 yet or are in the process of taking PNA2 right now, if you're doing it in C++, then pointers is one of those sources of pain in that class. So it's something to get familiar with. If you, at least in my opinion, if you understand what they represent and what's going on under the hood, that can be helpful in sort of managing the syntax, the syntactical complexities of pointers. C++ pointer syntax, some people find it very messy. All right, and then finally the usual stuff. So homework lab discussion as always, and then project 2 is out there. If it were me, I would start it sooner than later, just because the end of the semester, if you're taking more than one class, has other things that come due. So I can't make you, obviously, and I can't check on you that you are, but I'll just constantly encourage you to do so. All right, I'm going to switch over then and look at stuff in code. Just making sure you can see what I see. Okay. That open? Oh, I guess because I moved the little window down. Well, I don't want that there. I want it down here. There we go. I think I emptied this thing. Okay, so we are talking about allocating memory at runtime, and I'm going to put a static variable in here just so I can talk about the difference. This is week 13. Yeah. So when we declare things in this static section in HLA, and it's the same thing when you declare any variable in a high-level language, Go, C++, Python, whatever. These static variables are things that are set aside. The space for them is made in your program so that when you run this program, that memory space already exists And you can more or less think of your variable names as labels on memory locations. And we talked about this with direct addressing. Static variables are nice because they give you a label to refer to a memory location, and you don't have to mess with addresses to get to memory locations. So we like static variables because they're very convenient. They give us a convenient sort of plain language label in the form of the variable name. The other cool thing about statics is that the memory is set aside for them when the program runs, and then the memory is cleared up automatically for them when the program ends. This is also true for what HLA calls automatic local variables, but variables that you declare that are limited in scope. Basically, space for the variable will be created when it's needed, say when a function executes, and then when the function returns, the space that was used for the local variables is automatically cleaned up. So it's not that the manual memory languages don't have any kind of cleanup on variables. It's just that the dynamic allocations of memory don't have cleanup. Garbage collected languages, it's the dynamic memory allocations that are cleaned up for you. HLA is manual. But anyway, static variables, automatic local variables, those things, the space is set aside for them, and when they're no longer used, then that memory is cleaned up and handed back over to the operating system. So anyway, like X here. That X and the space for it in memory will be created when I run this program, and when I shut the program down, that memory will be kind of cleaned up for me automatically. But let's do, I'm not going to use any just yet. Let's just do some of the memory allocation stuff. So the most basics about memory allocations, and then I'll go back and read some documentation. The call to malloc. This is a memory allocation, and the argument that you specify is the number of bytes that are required. So let's just say I want 1 byte of memory. So this is dynamically allocated memory. It is still RAM, but because I allocated it dynamically, the space wasn't set aside for it when the program launched. The space will be provided by the operating system after the program begins to run, and then I need to give that space back to the operating system when I'm done with it. Yeah, that's a good, so Druid in chat asked the question about static variables. Can you sort of think of those as sort of the fixed memory cost of a program? And yeah, that's entirely accurate to say that. Statically allocated variables are sort of the fixed memory cost of your software. And then the dynamic allocations, like this mallocing of 1 byte, which is not very exciting, but if I malloc this 1 byte, then that is the runtime cost. So that's another little piece of RAM that wasn't set aside for your program when it launched, but will be provided to it. It's not guaranteed, by the way, to be provided to it. Mallocs can fail if the operating system doesn't have any more space to offer. We're not going to encounter that situation in our class, but in the real world, when you do dynamic allocations, you normally need to check to make sure that there actually was still free memory available for the operating system to give you. Oh, good. Yeah, so Druid followed up the fixed cost with the idea of the variable cost of memory. Yeah, so that's perfect. That's really good terminology. Okay, so what does a malloc do? It allocates a specified number of bytes. So this is 1 byte of memory. And I'm going to put the term untyped here. And what I mean by that is that a dynamic memory allocation has no association with any data type. It's just bytes in memory. And you can use it for anything that in this case, 1 byte can accommodate. So first thing I'm going to do, though, is point out to you that a malloc returns EAX which will be the address of the allocated memory. So when you call malloc, you have to immediately go fetch the value of EAX because it will contain the address out there of that dynamically allocated memory. And I'm just going to print it in hex because it doesn't really matter. So malloc will do that. And now I can use this 1 byte for whatever I want to use 1 byte for, as long as it matches 1 byte. So for example, I can do this. I can move a character into it. I'll just say data. Gotta dereference it. So I can use, I can move a character into it. By the way, the way that HLA compiler, which is helpful to sort of think about how compilers do their work. How does HLA know to consume 1 byte of memory here? The answer is because chars are 1 byte of data. So HLA can figure out by the single quotes around a character that what needs to happen is it needs to take 1 byte of data and copy it to this memory location. So here I am using indirect addressing to store some data in that dynamically allocated memory location. And then I'm using that address to fetch the data. I can also move it should let me get away with this, I think, as long as the HLA compiler, that one may give me an error. We'll find out here. In fact, let's just find out. That one may give me an error. Let's see if HLA can figure that out. It cannot. Oh, wait. It's complaining about this one, which is interesting. What was the complaint? Unexpected square bracket. In this case, I thought it would have been able to figure it out, but apparently it can't. So let's see if the compiler, if that helps the compiler do its job. Yeah, so in that case, I thought the compiler was going to figure out that that was a single character, but it didn't. So I had to tell the compiler that that's a character, a byte's worth of data. Now I'm getting the same error on line 15, which is where I expected to get it, because how would the compiler know that my intention is that this is only an 8-bit value? Sure, it can fit in 8 bits, but that doesn't necessarily mean that I want it represented in 8 bits. So in this case, there's not enough. I'm surprised about the character, but anyway, these compiler errors are really just telling me that the compiler doesn't know how much space I want, so I am having to tell it. So notice here, though, the point I'm trying to make really is I can put a character there because I have 1 byte of memory there. I can put an int 8 there because I have 1 byte of memory there. I can put an uns 8 there. Because I have a byte of memory there. It doesn't matter what the kind of data is when we're just talking about an untyped location in memory. The burden is on me to make sure that I communicate to HLA what the data is. I'm going to label these. This should be an uns 8. This should be an int 8. That wouldn't, okay, now they're lined up, and this should be a char. So it doesn't matter. The reason why I'm using untyped and the reason why I'm showing you these examples is because HLA, the processor doesn't care. The memory doesn't care what kind of data there is in this case. It's entirely a matter of the space that I have to work with, which is 1 byte. Which is another thing, by the way, that static variables do. At least in HLA they do. In fact, yeah, I guess that would be true in pretty much every language. Maybe not every language. Most languages. A static variable is gives the compiler information about what kind of data to expect and how much space is needed to accommodate it. So that's all kind of compiler information, data types, and that's great because languages, in my opinion at least, that have data types and the compiler enforces those data types, it helps you avoid mistakes at runtime. So you'd rather have the compiler issue an error than have a running piece of software do something terrible like cause the satellite to crash into the surface of Mars, which has happened. Okay, so there is my usages of the memory, and then the last thing I'm going to do is I'm going to free the allocated memory. So this is one thing that you do kind of get without having to do the extra calculation. When you call free, you supply the address where the allocated memory began, and the system has kept track for you. Thankfully, the operating system, no doubt, has kept track for you of how much memory it had given you from that location. So this free will be translated into the number of bytes that need to be released back to the operating system, which in our case is 1 byte. So let's see if I did all that right. And that's just kind of showing that the dynamically allocated memory has no data type attached to it, which means that I can use it for any kind of data that I want as long as the data fits. So there's my 3 usages of it. Same memory location over and over and over again, different type of data. Now you all know the real trick. I just forgot what I was going to say about that. What's the real trick? That'll come to me in a moment. Sorry, I lost my train of thought for just a moment. What's the real trick? I don't know. It'll come to me. Okay, so there is a basic alloc, and I'm going to mark it off, and then I'm going to comment it out so we don't have to look at it again. So be thinking about this. When we allocate memory, we allocate a number of bytes, and then those bytes don't represent a specific data type. They just represent the amount of space we have to work with, and we can use that memory in any way we want as long as the things that we want to put there fit. So let's do another example real quick. If I were to malloc 4 bytes, let's say. In fact, let's go read the documentation and let's start using, I think, the library versions of these things. Let's see. So there's let me see if I can speak this, read this question in chat. So why do we free the memory by using the address that we got when we had it allocated? So a malloc call requests memory from the operating system basically, and the operating system says, here's the memory that you requested. The operating system can say, can return null, by the way, or in some languages it'll cause an error if the amount of memory that you request is not available. But if the amount of memory that you request is available, then the operating system will set it aside for you and give you the address where that section of memory begins. So don't think of it as a variable or some number of variables. It is just a chunk of memory that is however many bytes it is, and I can use that chunk of memory however I want. The operating system, when it sets that memory aside for me, when I call free and tell the operating system, please, you can have this memory that you allocated to me starting here, the operating system remembers how much that was. So it's not garbage collection, but all the operating system needs to know is give me the address of the allocated block, and I will take it back for other purposes. So it's not variables per se, it's just a chunk of memory or a block of memory And the operating system, one of its tasks is to give me that memory and then to take it back when I release it and offer it up for other purposes on the system. So I don't know if that answers the question. So there's only one address of a dynamic memory allocation, unless you, yeah. So one memory allocation, one address, and whatever size of block of memory you requested based on how much memory you want to use. It has no association with a variable or some variables. That's entirely a matter of how you use that memory, which I'm going to do an example of here. So maybe this will help. Yeah, so you can store the address in other places, sure. So we can do this. Address keyword, and I can store the address here that I got. No. So the question is, do I have to clear? No, you don't. So you do not have to clean up the memory in terms of like zeroing it out or anything. You just tell the call to free tells the operating system, I'm done with this block of memory that starts here. Whatever is going on in there, that's not your, the operating system doesn't care. The operating system just knows, okay, that block of memory that used to be occupied by that piece of software, I can now allocate elsewhere as needed. Oh yeah, you are saying Canvas, because I meant to go read the documentation. Sorry. Okay, so let's go look at the memory module, because I want to change my calls to match the libraries. So HLA does have malloc and free. And that doesn't really, nothing's going to change other than I'm going to use the library calls just because I like the way they look better. So we're going to use the HLA mem.alloc call. It's exactly the same thing. But the reason why I want that is because I want then to show you later the mem.zalloc, which there is no other variation on that theme. And then we're also going to use mem. Where'd it go? Oh, these, wait. Okay, these are all the allocating ones. Size, mem.stat, mem.getref. I'm just going to have to search it. Free. Oh my gosh. Dot free? Sure are a lot of them. There's mem.free. Keep going. I passed it. Okay, here it is. So I'm going to start using the library function calls only for consistency's sake, so that when we start using zalloc, it'll be mem.alloc, mem.zalloc, mem.free, so that it'll all just kind of look and feel the same throughout. Okay, so let me switch back over. And I don't know if I'm answering the question about deallocating satisfactorily or not, but we get this block of memory. And I'm going to go ahead and print it just to show you that the operating system is just going to give me that memory, and whatever happens to be there is there right now. So let's change this to mem.alloc so it will start to look more consistent. It's the same setup. How many bytes do I want? I want 4 bytes. I'm going to go ahead and store the address off to the side just so we can get used to seeing that. And then I'm going to print the memory in that location. And I have kind of multiple ways to do that, but it's 4 bytes. So I'm just going to pick a 4-byte data type here so that I can look at the data in all 4 bytes. In fact, why don't we just look at it raw? I'm going to have to tell it how many bytes I want. So let's grab 4 bytes and just look at it as raw data. Okay, so let me see if let me follow up on some questions here. Did I switch back? I didn't. This nom. Thank you. Sorry, I've been typing away. So all I did though is I added a dword variable, a 32-bit raw data variable, so that I can store the address of the allocated memory block, which in this case is 4 bytes. I'm using mem.alloc now because I think it'll be easier for you eventually if we use mem.alloc, and then I'll show you mem.zalloc in a moment, and then mem.free. Even though malloc and free are the same as mem.alloc and mem.free. Anyway, hopefully that makes sense. So I've stored the address to the side, and then I'm just going to look at the raw hex data by typing it to dword. The data type in this case communicates to HLA how much memory I want to look at, and this is 32 bits. So I want to go to this memory location and look at just the raw 32 bits of data as hex. All right, so another chat question. So we zero out EAX, but to deallocate we have to free. What instruction would be used to free the memory allocated? See, static, malloc, move. Okay, so in chat the question is, I'll go ahead and do it here, Druid, and I think this will answer the question. So do you have you do. So you have my array instead of address. So you can mem.free on the address even if it's not in a register, thankfully. So mem.free will work on the address data presented to it in a register or in a variable. So I allocate the memory, I set aside the address in a variable, and then when I'm done with it, I will use that same variable actually for the process of free. So I think that probably, no. So Druid is asking, would I also have to do this? And the answer is no. I don't also have to do a mem.free on EAX. Mem.free is an address, and you're telling the operating system the block of memory at this address, I'm done with it. It doesn't matter how the address gets communicated to the operating system, if it's as a variable or in a register. Remember, the register is just the address, and the address is also just the address. So you mem.free, you communicate an address, and the block that's associated with that address is freed. It doesn't matter if it was communicated having been stored in a variable or communicated having been stored in a register. Remember, registers are really just built-in 32-bit variables. Okay. So hopefully that answers that question. The free is you give it the address, either having stored it in a static variable, which is what I've done here, or having stored it or kept track of it in a register. It's still just the address of the allocated memory. Okay, so hopefully everyone understands. So this is following up on another question. So what's in the memory? In this case, it's zeros, which is lucky. I should put a new line here. In this case, the allocated memory was all zeros, but it's not guaranteed to be. So mem.alloc does not guarantee that you're going to get zeroed out memory. All it does is guarantee that you're going to, well, it doesn't even guarantee you're going to get memory, but it says basically you ask for this many bytes, hopefully you get that many bytes, and what's in those bytes is completely unpredictable off of a mem.alloc. Okay, yeah, I see the comment, Druid, that we can follow up and sort of dig deeper as needed in office hours. So yeah, perfect. Okay, so allocate memory. In this case, I'm storing the address, even though I don't really need to for this tiny little example. But when you get to project 2, you're going to need to store that address because you don't want to rely on a register being your dynamically allocated memory over time, because the register has a good chance of being overwritten, which means you have a good chance of losing that memory address, which means that you have a good chance of not being able to get back to your data at that memory location. And it also means you have a good chance of not being able to deallocate or free the memory, which means that you may end up causing a memory leak. Okay, so this is just what's the raw data. But if we think about 4 bytes, I have a variety of options. I can store, for example, I can treat it like an array. So I could do this just as an example. So I could treat it as, oh, let's say, I'll just put some numbers in it. No, let's put characters. It's more fun. A type char EAX. So I could treat this 4 bytes as a 4 character array if I wanted to. Got to make some adjustments here. Well, let me just add an offset. I hope it does. I think it will. Let me compile that before I go on to make sure that it is, in fact, going to let me do that. Okay, it will. So I'm just going to go to that address. I'm going to put a chart, the first memory location. I'm going to move over 1 byte for the next char, move over 2 bytes for the second or third, and then move over 3 bytes. So I can take these 4 bytes in this block, and I can use them as a size 4 array for 1 byte kinds of things. I can even loop them if I want to. So for move 0 to ECX, ECX less than 4, and ECX E, why won't you do it? ECX, there we go. Do put I can scale it to 1 byte if I want, even though it's not really required. I'm just going to put spaces. Something's wrong. Oh, I see it. So I just wanted to show you here, this 4 bytes of memory has no data type associated with it. So I can do anything with it that I want that would fit in 4 bytes. So I could put, for example, 4 characters in it, which I'm then printing out. I'm doing a scaling, even though it's not required for a 1 byte thing. So there's my 4 bytes of data. I could use it instead if I wanted. As let's see. So if we want to do int 16s, we'll do something higher. So we'll just do like negative 200 so I could instead use it as a size 2 array. Here I need to move over 2 bytes because they're consuming 2 bytes at a time. So now I'm using that same block of memory for a size 2 array of int 16s. I'm going to steal my own code here and make an adjustment. So less than 2. These will be int 16s. This will be a scale of 2. Doesn't really matter. The system does not care until I make a sizing mistake of some sort. But it's a block of memory. It's 4 bytes. I can do 4 1 byte things. I can do 2 2 byte things. I can do a single 1 byte or 4 byte thing rather. I can use it in any of those configurations that I want to because it's just 4 bytes of memory. There's no data type attached to it. I could use it for chars, int 8, uns 8, or a mix thereof. As long as I, the programmer, remember the correct typecast, it'll all work. 2 2-byte things, so 2 int 16s. Notice that I'm moving over by 2 bytes at a time, or 1 4-byte thing. I chose values, same thing I talked about last week. So my values here were carefully chosen so that if I wanted to make sure I didn't pick something here that didn't have to be int 16. So if I put -1 here, that I'm less likely to expose a mistake. If I intend an int 16, then I should choose a value that would trigger a mistake if it's not int 16. Yeah, so someone in chat asked online, I think 26 is what you're referring to. Could I say ECX less than or equal to 1? You can. That's not sort of, um, most programmers are going to do it less than 2. So less than and equal or equal to 1 works just fine. The standard practice is less than the size of the thing. Because we all know that zero-based indexing means that you need to stop 1 short when you're indexing of the size. So we usually say the iterator less than the size, which we know means from 0 all the way up to the last index. But that's not to say that you can't do it as less than or equal to 1. It's just people don't generally do it that way. Okay, so hopefully everyone follows here. 4 bytes of memory, no data type that's going to be imposed on me by the system, by HLA's compiler, so I can use it for 4 1-byte things. In this case, I used it for 2 2-byte things. Notice the scaling factor is changed. Notice also that I offset by 2 bytes for the second item, whereas in these I move over 1 byte at a time, and then I could use it for 1 4-byte thing. All good to HLA and the processor because it's just 4 bytes of data, and I can carve it up however I want to. So there's my 4 characters, my 2 int 16s, and my 1 uns 32. And I picked values, so if I want to test that I'm doing uns 32s right, then I should pick a value that can't be anything other than an uns 32, or at least somewhere in the territory. So if I put 0 or a 1 here, well, that's not really a good test. I'm not going to trigger any errors. Okay, so there's mem.alloc, there's mem.free when I am done. So notice I use the address, which really the address is only useful for these kinds of purposes. I can't use the address variable to actually dereference. I have to have it in a register. But I can use the address for long-term tracking of my dynamic block of memory, so that when I'm done with it, I can use the address to deallocate it. I can also use these addresses to pass addresses to procedures, which is handy. Okay, so there's a block of memory. Unfortunately, this one keeps coming up. Let's put these back. In fact, let's just repeat the whole thing. Let's see what happens if I immediately reallocate right here. And then I'm going to look at the raw data. And then I'm going to mem.free on this second one. Because I want to see if I can I want to see if I can prove that this dynamically allocated memory is not guaranteed to be zeroed out for you. So I'm kind of hoping the operating system, yeah, so the first allocation I got zeros, and that's nice, but the second allocation I got garbage. So when you look at the raw data from a mem.alloc, there is no guarantee that it's going to have zeros in it. It can just be garbage from the last time it was used. My guess would be that is probably, I got reallocated the same block of memory that I allocated the first time, and then freed, and then requested another 4-byte block and got the same block back from the operating system that now has my old garbage in it. So the reason I did this in part, the second one, the second data had garbage, which means that the dynamic memory had garbage. In HLA, there is a library routine called залloc, and what залloc does is it zeroes out the memory block for you. This doesn't always necessarily matter that you have it zeroed out, but it's handy that HLA libraries have this mechanism where I can dynamically allocate a block and have the library routine zero it out for me. So now when I recompile this and run it, the second data is also going to be zeroed out. And that's because of the mem.zalloc that I used here. So that's handy. honestly, I can't think of a reason why you shouldn't do that in your second project. In fact, I think your second project may ask that you do that. But I also just wanted you to see this is not something that's always available in every programming language and its libraries. HLA happens to have a allocate and zero, but HLA also has the more kind of traditional allocate and hopefully I don't get garbage. Okay, so not a whole lot to add to all these things, but let's go ahead and add a few more. What did I have? Let's see what I free. Oh, the at size thing. Yeah, so the at size thing. I'll go ahead and do it here so I can say malloc. So this is an HLA operation, but you can actually use it to have HLA compute. So this is kind of a special syntax, but what you're saying is I want 10 of int32s, which is 4 bytes a pop, which is 40 bytes. That's what will be allocated to me, is 40 bytes. I'm going to go ahead and use my address variable. Why not? So these, I forgot to use mem.alloc. All of these memory allocators return the requested memory block address in EAX. That's just how HLA libraries were written to work. So it is good practice to take that address that is the beginning of your newly allocated block of memory and store it somewhere safe, so that you don't lose it, so that you don't lose your data and or cause a memory leak. And it's not a bad habit to go ahead and identify the point where you can give it back to the operating system and then go and insert your code in between. So this is 4 bytes times 10 is 40 bytes of memory. Just because I use the size of int32 doesn't mean that those 40 bytes of memory are int32 memory. They're still just raw 40 bytes of memory. This is just a convenience in HLA for doing the scaling part for you. I'm going to just replace this with something manual so you can see. But this is an HLA convenience. It's also available, by the way, in the C language. That's going to be 4 bytes for an int32 times 10, which you can use in this context, will give you 40 bytes of dynamically allocated memory, which you can use for 41 byte things, 22 byte things, 10 4-byte things, and any combination thereof that you might be able to squeeze into those 40 bytes. So you could have a character followed by an uns32 followed by an int16. As long as they all fit, and as long as you are able to compute the correct offsets, you can do all those things. I mean, it's kind of silly to do it, but you could do it because it's just 40 bytes of raw memory that can be used for anything. Okay, that's all I cared to do with that. Although, I mean, I'm going to give you some help here. Why not? Let's see. Is it rand.randomize, I think? I think it's rand.randomize. So I'm going to go ahead and populate this thing with a random data. So for move 0 ECX less than 10. So I'm going to do 4 byte things, which means I'm going to have 10 of them. I'm going to populate it first, and then I'm going to print it just to see what it looks like. So, oh, this is a bummer, actually. So this is something to look, I'm glad I just did this. So I'm going to be doing rand.urange. I forget how this works. Maybe someone in chat can remind me if I'm doing, let me see if this compiles. My gut tells me I'm doing something wrong. Yeah, it wants parameters. Was it 2 parameters? I'm just guessing. I'm going to look it up if I get stuck with, okay, I guess it was 2 parameters. This is probably between 1 and 100. Let's say between 1 and 1,000 to, in fact, let's get it up to 1 in a million. So we can get it up into the, what could possibly be int32s. Okay, so I just want, now that I have this, I want to point this out to you. Ran.urange overwrites EAX. So that's unfortunate because I have to have this address in a register. But it can't be EAX because ran.urange needs EAX. Can't be ECX because I'm using that for my loop counter. So I'm actually going to have that memory location loaded up into EBX, knowing that I am going to need to overwrite EAX with my random numbers. Hopefully that all makes sense. Why move it into address? Long-term storage, and then somewhere way down the line, I'm going to use that stored address in that variable to free the memory. That minimizes my opportunities for making a huge mistake with that. Why do I also copy it to EBX? Because I want to get random numbers and they're going to overwrite EAX, and there's nothing I can do to stop HLA from doing that. Why not ECX? Because I'm already using that for my loop counter. Could this be EDX? It certainly could. EDX would work fine. I just need to have a register that will reliably not be overwritten for me. The other thing I could do, by the way, no, it's just not going to work out that way. So yeah, this is the smart thing to do. And then I'm going to move the random value. Now EAX is no longer an address. It is a random value. I'm going to move it into EBX plus ECX, and each one of these is 4 bytes a pop. So there I'm populating my array with, these will all be positive values, that's fine, with random numbers. Yeah, so Druid asks, what's this ran.randomize? That's the seed. So that seed's the random number generator. And then I'm going to print it. Don't need the random to print. I do need this though, so I'm going to keep it. This time with the typecast. Yeah, int 32s is what I wanted. Put a space, and then I'll hold on to the end for the new line. So here's randomly populating an array. I'll separate those out so that they make more sense. So this is my initial setup. I'm using the HLA at size thing to know that int32s are 4 bytes. I could just as easily have done this because I know. But I wanted you to see the application of an at size, which you can use with this multiplication symbol as its partner, just like you do when you scale. So this is kind of like scaling to 10 of 4 byte things, which is 40 bytes. Long-term storage of the address so that the free later is guaranteed to work. Moving EAX over to EBX so these random numbers don't wipe out my address value. And then I'm going to populate with the randomly generated EAX, and then base address, index, scale per item. And then I do the same thing to print. So I'm going to just leave EBX with its address, base address, index, scale per item, and then the type to match the earlier type that I specified in 32. Hopefully I get. Are those going to fit on the screen? Yeah, more or less. More or less those fit on the screen. And then I had the free. All right, one more example around this just so you can see kind of some setup that you're going to need for the second project. So I'm going to do this. I'm going to add another variable, and I'm going to let the user say how many integers they want, and I'm going to move the new line to be up and down here. So I just want you to see, so can we do this memory allocation not even knowing what size we're going to allocate to start? And the answer is yes, we can. So the way we would do that is we'd say, how many int32 do you want? We will do a standard in.getU32, and then we will take that and move it into our size variable. So they'll type 5 or 10 or whatever. I don't think this will work, but let's try it. I'm pretty sure that this is not going to work. If it does work, that'd be pretty cool. I don't think it works this way, but if it does, then we'll just say, cool, that works. But I'm pretty sure I'm going to get a compiler error. Yeah. So one of the problems of this neat little trick is that you can't put a variable in there, which is a bummer. Can I put a register in there? Let's see. You cannot. So this has limited utility because you have to hard code the size. You can't do it as a variable. So then how would we get around this problem? In other words, what do we allocate? So the way you do this is you're just going to have to say move at size int32. I think this will work, into EAX, and then mul size against it. And then I will alloc EAX. Now there's some funky stuff going on here, and let me make sure it compiles before I describe it. Okay, so project 2, how would this work? We're going to ask them, how many of them do you want? We will read in how many they want. We will store that away as the size. We're going to need that later. Now we can use this at size and load up part of our multiplication problem into EAX. Why EAX? Because mul is hardwired to EAX. So this is one of those moments in the semester where kind of knowing how central EAX is in HLA is helpful. But also it's an x86 issue. The mul instruction in x86 is hardwired to EAX, just like the div instruction is hardwired to certain registers. So I'm going to put whatever they input, let's say 10. I want 10 of them. So that 10, well, first I'm going to put 4 bytes per into EAX, and then I'm going to mul that 10 times what's in EAX, which will be 4, which this should yield an EAX that has 40 in it. So I'm going to allocate. In fact, let's print it out. So I'm going to put allocating. So you can see kind of this sequence, how crazy it gets with EAX. So EAX is the 4 bytes. Multiply EAX equals EAX times size, which if I were to input 10 would be 40. This is going to print out, I'm about to allocate 40 bytes for you. And then I do a mem.alloc 40. The weird thing about this is that I pass EAX as the argument. I get EAX back as the address. Oh, I already had that. That's already down here. So why EAX for the mul? Because you have to. Do I have to use mem.alloc EAX? I don't, but it's convenient because the mul landed there. But I just have to know that when I mem.alloc the number of bytes that I have calculated into EAX, what I get back is EAX overwritten with the address of that allocated block of memory. The other thing I have to change then is that 10. That's now the size that they input. This is now the size that they input. And for information's sake, let's add some index information. All right, so now I will see which index I'm on and the value that is at it. Same scale, that doesn't change. I could probably use at size int32 here. Okay, anyway, I wanted you to see this little sequence because this is a project 2 sequence. How many do you want? I'm going to have to use multiply to scale to the number of bytes required based on the size of the data that I want. So if I want however many they want in 32s, then I need to multiply how many they want by how many bytes each of them consumes. Print this out, and then the rest. Okay, so let's try it, and I'll tell you as I'm running it what I expect to see. All right, so if I put a 5 here, it's going to be 5 times the size of an int32, which is 4, which should say that it's allocating 20 bytes, which should mean it's going to populate indexes 0 to 19 with a random integer, and then it's going to print 0 to 19. Oh, no, 0 to 4, not 19. 0 to 4. So there's the random values. Allocating 20 bytes, that's what I expected. And then we don't see it, but we could print it out, though, if we wanted. So standard out.put freeing the memory block at okay, so I'm going to take 7 this time. So the mul should end up with 28 bytes. 7 that I want times 4 each bytes is 28 bytes. I'll get indexes 0 to 6. And the memory address, which doesn't really matter to me, but that was the address where the block had been allocated. And then I put a little note for myself where I was doing the freeing of it. So I can see how many I'm allocating, then I use it, and then I can see that I'm freeing it and what address that was, where that memory lived. Okay. That's most of that kind of stuff. I'm going to go look at the lab real quick and see if there's any surprises. So you won't see me switch over. I'm going to go grab the lab code, which is here. All right, so let's study this. Let me make sure you're still seeing what I see. You are still seeing what I see. Okay, so you probably can guess, but I'll go ahead and just tell you what these things mean. So this numbers as a dword variable at this point is strongly suggesting that this is probably going to be used to store an address. Dword is 32 bits. Addresses are 32 bits for us. So this is probably going to be an address, and the name of it suggests that it's an address of a collection of things, i.e. numbers. So this is going to be where we do long-term storage of our dynamically allocated array. And the reason why we do long-term storage is because then we don't screw up the free. We can just do a mem.free with numbers in this case, and know that it better have the address that I need to be deallocated. And then I'm also going to track the size that was requested. There's really no other way to do this. You're just going to have to track how big of an array was requested by the user. And you're just going to have to store that in a variable so that you can use it as I used it in the earlier example, which reminds me I should make sure that gets to where you can access it on the lecture page. Okay. So hopefully those make sense. I didn't name it address. I could have called it numbers because when I was setting this up, I was thinking this is my numbers array or the address of my numbers array. So I'll just call it that. All right. So get int 16. That one's already been implemented, but there's a good chance that this is designed to be an int 16 array, which means it's going to be 2 bytes per. Here's a get uns 32. Why is there a get uns 32 in here? Because where is it? The size is an uns 32. Why does the size need to be an uns 32? Because we are going to be using the size. I'm going to switch over real quick. We're going to be using the size in this kind of context, where we need ECX to be an address index, which means it has to be 32-bit ECX. And we need to stop that addressing index by comparing it against the size. So I cannot do this ECX to size comparison if size is not a 32-bit thing. And because the size of an array will never be negative, I made it uns 32. So there's a lot of moving parts there. The size is uns 32 because I know that I'm going to have to eventually use it in a loop where I am setting up to access memory, which has to be done in 32-bit stuff. So that's why that is that way, which is confusing, but that's just, I screwed something up in here. Something looks wrong. Okay, I think I accidentally just deleted something. All right, so this get uns 32 is for the size, and it may be for some index values as well. Go again, the same old go again as always, print. So printing in this case, there's only one kind of data, so you only have to worry about one loop, no decision and no if statement inside of it, just one loop, one size, one scale factor. So this one is going to be a loop over int 16. You have a size variable, and you know that you need to scale to 2 bytes per because this is an int 16 array. So you've already got the base address moved into EBX for you. The address and the size are coming in, by the way, as parameters. So this will be the address of the desired array. This will be the size of the desired array, but you're going to write it for an int 16 array, scale factor of 2. Editing. Oh, this is what's messing me up, is some of the tabbing has just kind of got goofy. Here's another get uns 32 because we're using it to get an index to access a specific item in the array for editing purposes. This get int 16 is because we're getting a new value. Those are cruddy values. Those are poorly selected values. I'm not happy with that, but oh, I know why. There's a future purpose in mind for that. But these are not good values to test with on an int 16 because these also would fit in an int 8. This one's already been done for you, so you don't have to worry about that, although I did this one badly. Edit array has already been done for you. Finding the maximum. Ooh, maybe I should give you a hint on this. I think I should. I have time. I'm going to go ahead and do it. So here comes a gift. Oh, this is easy. Adder, that's this guy, into EBX as directed. No problem. All right, so why are these just all out of whack? I don't know. Copy the first value. So this is having you set up for an algorithm. It's called a greedy algorithm if you want to look it up, but the idea of this algorithm is if I have an array, an unsorted array of values, how do I find the largest one? Well, one easy way to do it is you take the first element and you assume it's the largest one, and then you compare it with every other element that follows. And if you find one that's larger, then you swap out what you think is the larger one with the new larger value, and you keep going. When you get to the end, what you will have is the largest value. So copy the first value from the array into AX. Easy enough. EBX. So why am I not doing any offsets? Because if I go to the base address of the block and I dereference it, I get the first thing. And if I move it into AX, I get the first 16 bits, which matches the size int 16, which I know the array to be from context. So this is the first value. It's an int 16, and I just need the data here, and then when I do comparisons, I'll start doing typecasting. So this gives me the first 16 bits of this memory block, or this array in this case, which will be the first value. Use a for loop to look through the values starting at 1. Why 1? Because we already grabbed the first one, and now we'll look through the rest. So for move 0 to ECX less than size, which was passed in as a parameter, and happily was a 32-bit thing so that this loop works. Increment ECX, do X one of those. So what's the question? If I find a larger value than AX, then I will keep it. So this is how I would write this. So if, I'm going to typecast them here to make sure that I get the negative positive things interpreted correctly. So EBX plus, oops, start at 1. So EBX plus ECX times 2, they're int 16s, is greater than, I'm going to typecast this one too, just to be on the safe side, then. So what I've done so far, I forgot to start at 1 even though it told me to. The reason why I start at 1 and not 0 is because I already grabbed the 0th value. That's basically this. And then I'm going to look through the rest. And as I'm looking, I'm going to compare. This is memory. So this is a memory piece of data to a register piece of data. So I can compare memory to register. How do I know this one's memory? It's because it's got the square brackets, which means I'm dereferencing a memory location. So if this value in memory is bigger than this AX value, which should be my current largest value, assuming that the first one was largest, well, time to make a change. I'll just take that data and make that the new largest value, and then I'll keep going. So as I move along the array, AX is going to be whatever I think the highest value is, and whenever I find something bigger, then I'm going to swap that into AX so that as I continue to look, now it's a new higher value. And when I get to the end, I should have the largest value. It says to return it in AX, which means I should just leave it alone. Just leave it sitting in AX. That's what's expected. So I'm going to leave that sitting on the screen. If you want to pass it around, that was like at 2:10 p.m. and beyond. Or someone can flag it in Twitch or something. So that one, I would prefer that people watch the lecture and watch the lecture video. So I'm going to sit here and let you guys, if you can, take it down or just note kind of where it's happening. Because I think it would be, at the very least, since I wrote the whole thing, that I have you at least kind of go through the process of typing it and looking at it and thinking about it, as opposed to just a copy and paste and I don't care. Okay, so there's Max. That, by the way, is needed on your project too. So that is a thing that you want for project 2. You will be able to make a min off of it for project 2 very easily, I would think. All right, what else is there? Create array. So we just did this process, and I will upload the earlier samples that have all that process in it so you can find that, where I did exactly that thing in the sample code today. Here's the allocating the memory. Here is the storing the address in my numbers variable so that I can come back to the numbers variable later for the required free. And here's where I do the required free. And then I do a 0 on the address, which kind of nulls out the pointer. I think that's everything. It is. There's 8 items in there, and I just did 3 of them. So 3 of them? I did 3 of them. So there's 5 left. Okay, that's where I'm going to stop. So that does get me through a few minutes early today. So there's my project 2 tips. You are seeing in this lab and in my samples for project 2 How do I ask the user for the size that they want? How do they use that to allocate the required memory? How do I allocate the memory? How do I free the memory? How do I loop to populate randomly the memory? How do I loop to print? How do I compute the maximum value? Like a whole bunch of the second project got done just in the last hour and 20 minutes. So hopefully that's of high value to you. I also, my closing thought about this is if I had shown you this code at the beginning of the semester, this is just for a way for you to kind of measure your own progress. That I bet all of you watching can look at this code and for the most part make sense of it. You know that the square brackets are somehow accessing memory. You know what the typecasts are designed to do to make sure that we're interpreting the data per the data type. You know what the scaling factors are there for. So that's, you know what the pushes and pops are meant to do. So to me, I hope that you have that sense of learning and whatever kind of progress ever you want to measure it, that you can look at a screen of code like this and not just be what in the heck is all that, but kind of actually be able to read it and make sense of it is a big deal. That's not easy stuff to read. Okay, I think that's it for me. I'll sit here for a sec, leaving this on the screen for those of you transcribing it if there's any remaining questions. So don't forget, next week I will do a live stream as always, but it will be a review live stream. So that would be a great chance if you are a live stream attender to bring in questions if you want to ask them, because I won't have tons of content to cover. I'm just going to kind of quickly list out, here's what we've done, here's the things that are needed for project 2, and that will be the review. But you won't have discussion next week, week 14. You won't have lab week 14. You won't have homework week 14. I hope I'm correct in saying all that. Let's switch over and double check, because I'm saying all that and then I'm going to be sad if I'm wrong. Nope. So notice week 14 just has a review page. If I do manage to generate any code samples, I'll post them, and I will post whatever I do for lecture during the live stream. Okay, that is it. Guess I like talking. Thanks for being here. If you were here for the live stream, I appreciate it. I appreciate the questions as always. They are good for all of us to hear and for me to at least do my best to answer them. And with that, I'll wish you a good week. And hopefully I'll see some of you next week for the review and some more kind of talk about what we need for project 2. Take care.